This is our third example for our bearing stresses. The lap joint shown in figure P-126 is fastened by 4 3/4 inches diameter rivets. Calculate the maximum safe load P that can be applied if the shearing stress in the rivets is limited to 14 ksi and the bearing stress in the plates is limited to 18 ksi. Assume the applied load is uniformly distributed among the 4 rivets. So the applied load is said to be uniformly distributed among the 4 rivets. That means we will always use our 4 rivets because that is what we are gonna use. We are gonna look for. So for example, if we are, it is not the maximum or minimum but the average. That simplifies it. So for our shear, let us just take the location of our shear. Should of course at the in between the plates, and let us take a single rivet so that we can expose the forces. Note that we must multiply it by 4 later because we are looking for the average. So our V is equals to our tau, which is 14 ksi, over, let us write here our area. This is a circular, pi over 4. So I forgot to write the diameter, which is 3/4 inch. You can cancel our inch squared. So V, or our load, this is for a single rivet. So 14 multiplied to pi over 4, or diameter squared, which is, let us multiply by 4. I will write. Our answer is 24.74 kips. That is for our shear. So for our bearing, we are still considering the average. So let us just try to calculate for a single one. Let us draw the figure in 3D so that we can see the reaction of the bodies. We'll shade the part where the largest area where the plate and the rivet will go against each other. The contact pressure between the rivet and the plate would have the largest area. So that our thickness 7/8, and our diameter is 3/4. So our blue is simply a rectangular. You can just multiply it. So that's 75. Okay, 3/4. 21/32 inches squared. So let us write our formula. That should be A sub B for specifying that it is our bearing. 18 kips per inch squared. Our load, inches squared. We can cancel our inches. 18 multiplied to 21/32, and that is for a single bearing. It is for a single connection. It is for a single connection. The contact pressure between a single rivet and a plate. So we need to multiply it by 4. We would have a load of 47.25, which is in kips. So comparing to our shear load, average shear load, the shear load would of course be smaller, and that means it is our safe load. So we can use our safe load to calculate for our normal, right? For our normal. So I will shade the area perpendicular to the P that the normal will resist, that the normal will use to resist against our P. So I will denote it as P sub n, the force. So for our normal, using our safe load that we calculated, the shear, using our shear because it is smaller. So our area is E sub n, base times height. Our base is 4 inches. So I will write the dimension again. 4 inches minus the diameter. The diameter of a single rivet. E sub n that's 75 multiplied to 7/8. Our answer is 91/32 inches squared. So note that our V, or which is equals to P, is already the load using the 4 rivets. Right? So if we consider a single area for our normal, since the P is already the average of the average load that the 4 rivets can resist, we can already consider a single area. So we do not need to multiply it to 4. So our normal would be 8.7 kips. That's all for this problem. For our fourth example, in the clevis shown in figure 1-1b, find the minimum bolt diameter and the minimum thickness of each yoke that will support a load of 14 kips without exceeding a shearing stress of 12 ksi and the bearing stress of 20 ksi. So we have here a clevis, and looking at the figure, we have, let us first write the given. So P is equals to V, and we have a limitation for our shearing and bearing. So we can see that we have 3 contact areas between the first figure, the clevis, and the clevis pin. So I will, since at the clevis pin and at the clevis we have the same, which is symmetrical, 2 and 3, figure 2 and 3, I will put them as equals. So we can try to solve for our shear, using our shear, the load using our shear, using figure 1 and figure 2. But since figure 2 is equals to figure 3, we can multiply it. Figure 2 and 3 are a single structure. So we can see that at the clevis, before it was divided into 2, it was a single P, and at 2 and 3 it was distributed. So that's all. So our tau, so we're gonna use our figure 1. So we already answered this type. We know that it is in double shear. So our V, so that is P is equals to V is only when it is in single shear, but when P is equals to 2V, it is already double shear. 2V is double shear. So we can substitute our 14 kips. So our tau is 12 KSI. Our P, which is equals to 2V, is 14 kips. So we need to multiply our area by 2 to make the equation in equilibrium. So our D is 14, that is 3 pi. So we have here 14 over 3 pi. Okay, we forgot to multiply the numerator, the area, by 2. So let us multiply it by 2, be 6 pi. Square root 14 over 6 pi. For D, let us use our calculator again. Is 0 that it is a very small 86, that's 16, that 18 inch squared. So let us try to calculate using our figure 2. So we can see that we have a single shear. The other side of the clevis would be unbearing. That is why the force is the structure is in equilibrium, right? So you can see, let's try to draw here. That our P was divided. So we have here, that is why at one of our bolt there will be only 0.5 P. So that is our V. Next is again some forces Y. Going up is positive, so 0.5 is going up, minus V equals 0. V is equal to 0.5. But since the two figures is symmetrical, or the P is originally a single one, figure 2 and 3 is originally a single entity or structure, we can multiply it by 2. So let us write, since figure 2 and is equals to figure 3, so 2V is equals to P. You can already see that it is in double shear, and it would of course have the same answer. So for our bearing, let us try to solve for our bearing. There would be, so let us draw another figure so that we can see where the bolt, how it is affecting our clevis by its bearing, how the contact pressure between the bolt and our clevis, our divided, the part of the clevis that is divided, are trying to put the structure in equilibrium. So we drawn our figure 2. So we can see that the metal from figure 1 or our load is trying to pull the right side of the clevis pin or the side near the load down or downwards. So the effect on the other side or the other edge is of course upwards. It is the opposite. So the load is trying to tilt the clevis pin, causing our P sub B, which is an internal force, or the clevis to cause another reaction or cause a surface reaction, making a contact pressure, and that is where our bearing is. So let us try to write the directions of our forces. So if we separate our clevis, we would have a reaction. We have our external force P, and if we summate forces so that the clevis would be in equilibrium, we would have our P over 2, or which we denoted as P sub A, as an internal force. And for the reaction of our clevis and the clevis pin, we denoted P sub B as the internal force of the clevis to the clevis pin, which is where our clevis pin is being pulled downwards by our external force P. So here we will try to draw another figure. So here we can see that our metal from figure 1 is pulling the clevis pin. I hope you can understand the illustration. So the location for our bearing would be at the both clevis pins, at the connection of our clevis pin and our clevis. I will encircle one bolt by blue so that we know. If we cut at the middle of the bolt, we will consider our largest area that is resisting the bearing, the contact pressure, and we would have the figure where we can see the area of the bearing and its dimensions. So let us shade the area, the maximum area, the contact between our clevis and our clevis pin, which is, so it is called a bolt because if we only consider the small part, it will become a bolt. So if we cut our clevis pin, it will become a bolt. So from our problem, it says a diameter bolt. Anyways, but they are the same. So our area, the contact is rectangular, and we can use our formula sigma sub B, or our bearing, is equals to P sub B over A sub B. So here, let us draw the other P sub B. So that is what I was talking about earlier. We did not draw. Anyways, you can already imagine the effect of our surface of tilting our clevis pin to the clevis. That is the effect. So P is of course equals to our P sub B. So our P sub B is 14 kips, and our area is D multiplied to T, which is, if we consider the other side or the other part of the clevis, would have we would need to consider two areas, because from the section that we cut only considers a single side. So considering our two sides, we can calculate. So it is thickness, minimum thickness for each yoke. So a yoke is simply a beam that is being held or supported by two supports. So our thickness is 0.40. That is all. Thank you.